Now that we've looked at the overall structure of a pipeline ADC, let's zoom in on a crucial building block that makes it all work, the switched capacitor circuit or SC circuit. This is a very common technique used in integrated circuits because it allows us to build very precise amplifiers and filters using only capacitors, switches, and op-amps, which are much easier to manufacture accurately on a chip than resistors. Looking at the diagram, you can see the key components listed on the right. We have switches, which are typically small transistors that act like on-off gates. We have capacitors, which store charge. We have an operational amplifier, or op-amp, which provides gain. And finally, the component that orchestrates everything is the two-phase non-overlapping clock generator. Let's look at the clock signals on the left, labeled phi, phi1, and phi2, phi2. The term non-overlapping is extremely important. It means that phi and phi2 are never high at the same time. There's always a small period where both are low. This prevents signals from accidentally passing through when they shouldn't and ensures charge is transferred in a very controlled manner. The operation of this circuit is broken down into two distinct phases, dictated by these clocks. First, we have the sample/reset phase. This occurs when the clock signal phi is high. When phi goes high, it acts like a command to close switches S, S2, S3, and S4. Let's trace the signal path. Switch S connects the input voltage V to the sampling capacitor C. At the same time, S2 connects the other plate of C to the op-amp's inverting input. This action captures, or samples, the input voltage by storing a proportional amount of charge on C. This is why it's called the sample phase. Simultaneously, switches S3 and S4 close. Notice they create a feedback loop around the op-amp, connecting its output directly back to its inverting input. This configuration forces the op-amp into what's called a unity gain buffer state, which effectively resets it and removes any charge stored on the feedback capacitor, C, from the previous cycle. This ensures we start each calculation from a known, clean state. So, this first phase is both for sampling the input and for resetting the amplifier. Next, after phi goes low and there's a brief pause, phi2 goes high. This initiates the second phase, the hold/amplification phase. Now, a different set of switches, S5, S6, and S7, are closed. The input V is now disconnected, so the charge on C is held. Switch S6 connects the left plate of C to ground. The charge that was stored on C now has to go somewhere, and it gets transferred through the op-amp's input to the feedback capacitor, C. This charge transfer process results in an amplified voltage at the output, E. The amount of amplification is determined by the ratio of the capacitors C and C. So, in this phase, the sampled voltage is held and amplified to produce the final output. In essence, this circuit performs a sample, hold, and amplification function in two clock phases. This precise, timed operation is the fundamental principle behind how each stage in a pipeline ADC processes the signal before passing it on. Continuing our look at this switched capacitor circuit, let's now focus on the timing and how it actually processes the signal. The waveform diagram on the right is really helpful for this. It shows our two clock signals, phi1 and phi2, the input voltage Vin, and the resulting output voltage, Vout. The first crucial point here is that the circuit samples the input voltage right at the falling edge of the phi1 clock signal. You can see on the graph where Vin is marked as V and V2. These are the specific voltage levels at the exact moments when phi1 transitions from high to low. At that instant, switch S1 opens, effectively trapping the input voltage's value as an amount of charge on the sampling capacitor, CS. So what happens next? In the following phase, when phi2 is high, the circuit reconfigures to amplify this captured value. Look at the Vout waveform. After the circuit samples V, the output settles to a new value, V, during the phi2 phase. Similarly, after sampling V2, the output becomes V2. You might also notice that the output signal is an inverted version of the input. When Vin is positive, Vout is negative. This is typical for this kind of op-amp circuit. And see how Vout is labeled reset to 0 during the phi1 phases? That's the reset phase we talked about, getting the op-amp ready for the next sample. Now, let's break down the physics of how this amplification works. It's based on a fundamental principle called conservation of charge. Essentially, the charge we sample doesn't just disappear, it gets moved. During the phi1 phase, when we're sampling, the charge collected on the sampling capacitor, let's call it Qs, is determined by the formula Q equals CV. So, Qs is equal to the sampling capacitance, Cs, multiplied by the input voltage, Vin. Then, during the phi2 phase, this stored charge is transferred entirely from Cs over to the feedback capacitor, Cf. The op-amp works to ensure all the charge moves. The charge now on the feedback capacitor, which we can call QH, is equal to its capacitance, Cf, times the output voltage, Vout. Because charge is conserved, the amount of charge we started with must equal the amount of charge we end up with. Therefore, Qs must equal QH. This gives us a simple equation, Cs times Vin equals Cf times Vout. If we just rearrange this formula to solve for Vout, we find that Vout equals the ratio of Cs over Cf multiplied by Vin. This leads to the final and most important takeaway. The gain of the circuit is precisely set by the ratio of the sampling capacitor, Cs, to the feedback capacitor, Cf. This is a brilliant technique for designing integrated circuits. Because manufacturing a capacitor with an exact absolute value is very hard, but manufacturing two capacitors so that their ratio is extremely accurate is much, much easier. This is how switched capacitor circuits can create very precise amplification, which is essential for building high-resolution analog-to-digital converters.